Now we're going to look at the alkylation of benzene via the Friedel reaction. This is very similar to the halogenation reaction. You need to be using probably aluminum trichloride or aluminum tribromide. It doesn't matter which. It depends on the halogen that is attached to the alkyl halide you're interested in using. And be aware that you are going to be producing a carbocation. So if you use a primary alkyl halide, you are very, very likely to undergo a hydride shift or methyl shift to produce a more stable carbocation. If you're using a secondary substrate, it may also rearrange to produce a tertiary carbocation. And if it's tertiary, you're not going to need to worry about it. So I thought it might be useful in this lesson to show you one that actually has a shift, because sometimes students don't think about those things. So we're going to look at one that has the shift. I'm assuming most of you remember how to make alkyl halides. We're going to keep it very general. There's an alkyl halide. And it needs to go in solution with the corresponding aluminum halide. And in this case, that'd be bromine. So you're going to have AlBr3. Just so you know, you typically could use an iron if you needed to as well. And again, we're talking about metal chemistry here. Metals can undergo several different stable oxidation states. So, like we saw with halogenation, the halogen, the bromine, will add to the aluminum to make the Lewis acid-Lewis base complex. This looks almost identical to what we saw before. This bromine has a positive charge, and so it would like to stabilize itself, so we're going to break the carbon-bromine bond, and bromine being the more electronegative, we'll take those electrons with it as this bond breaks, producing, in this particular case, a secondary carbocation, and AlBr4. Because this is a secondary carbocation, you need to think about potential shifts. And in this case, there is a way to do a hydride shift. There is a hydrogen next door. So you will do this hydride shift. And in this case, you will produce the tertiary carbocation. So this is actually the electrophile that we are going to be using in our reaction. But this is how you produce them. So if it's a stable enough carbocation on its own, go for it, use it. Don't worry about trying to do a shift. But if there is a shift that is possible, you need to do it. Now, if it's on a primary carbon, it will not dissociate from this complex directly. It can't. So it'll shift at the same time that this adds, because you can't produce a primary carbocation. So there are rearrangements that are possibilities. Typically, you don't ever do this kind of chemistry if you want a primary carbon to end up attached to your benzene ring. We're going to do something else because there's always a shift. If it's secondary, you may have some trouble. It's an issue because a shift may occur. But if it's tertiary, you're good to go. You don't need to worry about it at all. So just be aware of these issues as you're looking at these reactions. Shifts can cause some problems for you. Alright, so if you've got an aromatic ring, and we now put it in solution with the carbocation that we have generated, you have to have a really good electrophile to make a ring react, we can start doing some chemistry here. So the ring will act as the nucleophile and donate its electrons to the carbocation. As this occurs, we make our resonance stabilized carbocation intermediate. And again, we can draw resonance structures showing the delocalization of that positive charge through the aromatic ring. And again, be aware. You need to think about potentially other groups on the ring. If you have electron donating groups or electron withdrawing groups, they're going to direct this electrophilic addition to certain locations. If they are the positions that I've circled in blue, they are electron donating groups, and this would be an orthopara director. And again, note that the positive charge is on the carbons adjacent to those groups on the ring. So if you put an electron donating group at one of those locations, these would be the resonance structures you would expect to see. And if this is the case, with an electron donating group, you would have an extra resonance structure as you donate the lone pair into the ring. If, on the other hand, you had a group at the positions that I'm circling here in green, you are a meta-director, and you would only have these three resonance structures. There will be no fourth, and so you're not as stable. They go a little slower because you don't get, you don't want to put the two positive charges next to each other. Okay, let me redraw. Right? Sorry. I didn't do it right again. I'm really sorry. I'll try to get this done right for you. Sorry about that. There's where my electrons are in the ring. Okay. Now, at this point, your metal complex comes back into play, which in this case was the aluminum tetrabromide. The halogens are more electronegative than the aluminum, so when this complex breaks apart, the halogen will take the electrons with it. And it will use those electrons to remove the proton. Now, as that occurs, you take this pair of electrons and you will reintroduce the aromaticity in the ring. The really cool thing about this particular reaction is that you are able to make another carbon-carbon bond. So you may want to add this to your list of reactions that make carbon-carbon bonds. And this is really cool because you can make a carbon-carbon bond between, oops, I used aluminum. You can use to make a carbon-carbon bond between an sp3 and an sp2 hybridized carbon. So this is really cool for that reason and very useful.